All right. So, we let us go back to the Lagrangian once again. So, I hope all of you can write the Lagrangian. It is first the energy and the constraint. So, energy was, if you remember, again we are going back to spin orbital. After knowing how to do the spin integration, we are going back to the spin orbitals for a general Hartree-Fock equations. So, that is the reason we are doing. So, chi I, H chi I, this is the one particle summation over all the n spin orbitals, okay, plus half of antisymmetrized, we have written it minus sum over okay. So, I hope all of you can write this. Of course, this expression can be written in different form, and I have not written the exchange or Coulomb explicitly. I have used the antisymmetrized matrix. Of course, eventually we will expand it. So, then we said that we vary each of the chi I to chi I plus delta chi I. So, in infinitesimal change, and we make the first order change, which I call delta L, equal to 0. So, that is basically ensuring the stationary conditions. We discussed that last time, that if I just make first order change in the variable, the first order change in the functional represents the derivative, first order change divided by delta x represents the derivative. So, of course, I can put this equal to 0, it means derivative is equal to 0, right. So, that is my condition that I am going to put. So, then what we started to do is to write what will happen if I chi I changes to chi I plus delta chi I. Since these are the trial functional, so we put for every chi I some tilde, but again that is really a question of only symbol. So, I put everything as okay. Then we rewrite delta L. So, when I write delta L, I ensure that I take only the first order change, because that is the delta L. So, this is the first order change. So, if you look at the first order change, so I made chi I to chi I plus delta chi I. So, the first is delta chi I, H chi I plus sum over I, chi I H delta chi I. I am not writing the summation index exactly 1 to n every time, but I think it is obvious that these are 1 to n. So, I have two terms from this. There is no change, no first order change due to H change in H, because H does not depend on chi I. Okay, H is a fixed operator, and then we had plus half of. Now, to make sure that we understand what we are doing, we want to write everything explicitly. So, we wrote this as delta chi I chi j 1 by R12 chi I chi j. So, we had 4 terms, if you remember, and then you do the same thing. There are same thing on the right hand side. Okay, I will not complete this. And then we had the exchange. Okay, so the summation goes over. Then I have the exchange, which is now delta chi I chi j 1 by R12 chi j chi I plus, so this is minus, of course, this is within a full bracket, plus chi I delta chi j 1 by R12 chi j chi I, okay, and then 2 more terms, right. So, this is what we did, and the 2 more terms come basically from the differentiating the right hand side, delta chi I chi j, chi I delta chi j, and so on. Okay. So, I am not writing this. Now, we noticed on that day that this term is a conjugate of this term, complex conjugate of this term, because of the fact that H is Hermitian, and these two terms which I have left are conjugate of these two terms, and similarly these two terms which I have left on the right hand side are also conjugate of these two terms. So we decide to write this as delta L equal to delta chi I H chi I. So I will not write this conjugate term, plus half of sum over ij delta chi I chi j 1 by R12 chi I chi j plus chi I delta chi j 1 by R12 chi I chi j minus half sum over ij, sorry, delta chi I chi j. Sorry. Okay. So it is just writing it, don't worry, a plus complex conjugate, plus the whole thing complex conjugate. I mean, you have to be just careful in that. There is nothing great about it. You just have to ensure that the indices are right. So I am changing the first one and the second one. These ones I am not changing. Lambda, sorry. Here also the lambda is there similarly, of course. So I will have only one term from the lambda minus ij lambda ij delta chi I chi j plus conjugate. Okay. So make sure that this algebra looks long, but it is really nothing. Once you understand what you have to do, it is just manipulating the indices correctly and then seeing what is equal to what. That is the most important thing. So now what we will try to do is to look at these two terms. This term I have a sum over ij, okay, and this term also has a sum over ij. So if I sum these completely, not for each ij, but if I sum this completely and sum this completely, they are actually identical by dummy variable interchange ij, okay, or you can say both and 1 and 2 also coordinate interchange. So both interchanges are okay. If I sum over ij, they are dummy variables I and j. I can call I as j, j as I. Similarly, I can call coordinate 1 as 2, coordinate 2 as 1. So it's very easy to see that these two are actually identical. And in the very same way, in the exchange part, this is identical to this. So actual same way, this is identical to this, the exchange part. Exactly dummy variable interchange. So only one of them can be written with the factor half removed, okay, in each case. So what we will do, we will write only one of them and the factor half will remove. Remember, the way we are doing it is the following, that I am trying to first, if you want to really formally show that this is equal to this, you first want to bring this here. So write this as delta chi j chi I, chi j chi I. So that's a 1-2 interchange. Then call j as I as j. So first do 1-2 interchange, then do ij interchange, followed by this. So you will exactly get this, and what will happen, the delta chi j which is coming here will now become delta chi I will become chi j. So you will have exactly in the same form. Is it clear to everybody? So please understand how to manipulate the dummy variable. Once again, for a given ij, it is not same, because I am using this dummy variable ij, so it must be sum over ij this is equal to sum over ij this. That is important to note, okay. So first I my overriding interest is to bring all delta chi I on the left. So I want to bring the delta on the left. To do that, I am doing a 1-2 interchange. After I bring delta chi j on the left, I want to make it look like delta chi I. So I make ij interchange. It's very simple. Okay. So both that is also allowed because the whole thing I summed over ij. Okay. Again, of course, I repeat that within the sum for a given ij, this is not true. But this quantity summed up is same. Is it okay for everybody? I mean, these are very small algebra, but you should be very comfortable in doing it. So if you do this, then I can have a further simplification. And since these two terms are same, now I will not write half. So half will go off. So of course the first term remains as it is, delta chi I h chi I. And the second term, sum over ij, just one term, delta chi I chi j 1 by R12 chi I chi j minus sum over ij delta chi I chi j 1 by R12 chi j chi minus sum over ij lambda ij delta chi I chi j plus complex conjugate of all the terms. When you wrote the energy, we could remove the half by saying I less than j. Here also half is removed, but it is not I less than j. It is all I all j. So just note this little difference. Here half got removed in a different way because I have combined these two terms. So what looked like a very monstrous expression, 2 from here, 4 from Coulomb, 4 from exchange, and 2 from the Lagrange multiplier. So it almost 12 terms has now simply become 4 terms because I am writing this conjugate. So of course there are 8 terms actually. So but the 4 terms are relevant. Rest I can write as complex conjugate, and I have managed to write it in a way that the left hand side everywhere is delta chi. That is a trick because now I am going to use the variation, whatever I told. Okay. So essentially we said that the first part for making delta L equal to 0, it is sufficient to make this 0. So then we are writing the equation now. So the equation now becomes delta sum over I delta chi I h chi I tilde. Now I will put tilde since I have a chance to write the equation all over again. Sum over ij delta chi I chi j 1 by R12 chi I chi j minus sum over ij delta chi I chi j 1 by R12 chi j chi I minus sum over lambda ij delta chi I Okay, so that becomes your Hartree-Fock equation finally for all delta chi I. So this is a one way of writing the equation. This is also Hartree-Fock equation. So for all arbitrary delta chi I. So there are two arbitrariness, all I, all delta. I again repeat, for each spin orbital, all arbitrary delta. So that is the meaning of derivative. Remember, I said when x goes to x plus delta x can be arbitrary change, then delta y must be 0. Arbitrary means it can be any value. So when one dimension, you may have only one direction, but these are multi-dimensional problems. So I can have any way I can change delta x. Infinitesimal. Yeah, otherwise it is difficult to interpret. But actually, if I want first order, it doesn't have to be. I showed you. I think I again repeat what I showed, that if x goes to x plus delta x, now tell me where is infinitesimal coming here, okay? So f of x, delta f of x, so let us say f of x is x square, then what is delta f of x? 2x times delta x, correct? First order change. So that is equal to 0, which means 2x is equal to 0. What did I use? Infinitesimal. Did I actually use explicitly? No. So even if it was finite, what is the problem? I in fact said in the calculus they call it infinitesimal because they don't use first order change. They use, if you write this as f of x plus delta x, then you are in trouble. Then it is first order, second order, etc. Then they say minus f of x, which is the total change divided by delta x. Then you have to use limit delta x tends to 0. I think I clarified that. Because here second order terms are surviving, divide by delta x, you still have a terms which are delta x square, delta x cube, they have to be made 0. For the first order change, delta x term does not survive. Just like here, 2x delta x divided by delta x will simply give you 2x. So the derivative, first derivative can be expressed in two ways. One is total change of the function. This is total change of the function divided by the change in x as the change in x goes to 0. That is one way. Second way is that you simply change x to x plus delta x, don't care how much is the change. Consider only the first order change, divide by the change. They are identical. That is what I did first. So it is, of course, we are going to do infinitesimal change, but it is never really going to be used. It is not required. Okay. So when you said f of x, x square, I didn't quite understand. If I have a larger change also, it will be divided by delta x, it will be 2x. Okay. But the point here is that this delta x can be arbitrary change. That is the point that we are discussing. It can be any change in x, any direction, anywhere. It depends on what is x. It can be a vector, so in any direction, any change. Plus, minus, you understand? So arbitrary means the change can be positive, negative. So for any arbitrary change, I am saying that this delta L must be equal to 0. That is what we mean. And for all spin orbitals. So that is why I have underlined this delta and underlined this I. For all spin orbitals. Okay? Since it is for all spin orbitals, I make a sufficiency condition to say that within the summation over I, whatever exists, I can make it equal to 0. Then of course, if I sum over I, it is 0. Right? So one of the sufficiency condition is now, this is very important now, is that delta chi I, now summation over I will vanish. Delta chi I h chi I plus summation over j, everywhere summation of I am just going to take out. Delta chi I, sorry again tilde, delta chi I tilde, chi j tilde, 1 by R12, chi I tilde, chi j tilde. Note that now the half factor has already gone out because I am writing only one of those two terms. There are 4 terms, 2 of them are anyway complex conjugate. Out of the 2 also I am writing only one term. So there are a lot of small steps that I have written because of dummy variable interchange. So please try to remember all these small steps. Okay. So delta chi I tilde chi j minus sum over j, delta chi I tilde, chi j tilde, 1 by R12, chi j tilde, chi I tilde, because this is exchange, minus sum over j, lambda I j, delta chi I tilde, chi j tilde equal to 0. This is now a sufficiency condition, because if this is equal to 0, now all you need to do is to sum every term over I, that must also be equal to 0. So this is 0 for again all I. So I have now used this condition. So if this is 0, this is now, there is no summation over I. So I must write this, because this I is now a specific index. Because you may ask, which I? I am saying for all I it is 0. Then of course if I sum over I, each term, that must trivially be 0. But this is not a necessary condition, this is a sufficiency condition. Because of course necessary conditions are much more difficult to derive. Because there could have been a cancellation as I sum over I, so it could have still led to 0. So I am only using a sufficiency condition to write this Hartree equation. Is it clear? Okay. Now I am going to use the arbitrary of delta. So there are 2 steps. First I have used all I. Now for each I, I am going to say that this delta chi I star is arbitrary. Yes. So everything is sufficiency. Yeah, everything is sufficient. That's what I said. Everything is sufficiency condition. No, this delta chi I is not a sufficiency condition. This is I am changing. I don't know which one you are talking. This one. No, this is not a sufficient. Huh? What do you mean by that? Because this is what I want to do. This is a necessary condition because that is what the variation theorem is. That I change all delta chi I arbitrarily. It should be still 0. That is the variation theorem. Summation over all I is 0. No. The first term is summation over all I. No? So this is correct. There is no sufficiency condition assumed here. Sufficiency condition comes here because of the fact this sufficiency condition. There are two different sufficiency conditions. One is that this part is equal to 0. That's a sufficiency condition. Okay, but then I am talking of something more. So there are two sufficiency conditions. One is the fact that if this is 0, the conjugate is, so please try to understand very clearly. If this is 0, the conjugate is automatically 0. Now I am saying that sufficiency 1 has been assumed. So I have this equation. Now I am saying another sufficiency condition for each I, if this is 0, then also it is 0. So I have a sufficiency 1 and sufficiency 2. Sufficiency 1 is to merely leave out the complex conjugate. Sufficiency 2 is to say that for each I, this is equal to 0. So it has also come under sufficiency condition, but if you are saying that the sufficiency condition is that the conjugate I have left out, that is correct. So there is a sum over delta. Okay. So I have applied both the sufficiency condition. One is that the real part is 0 or whatever, this I am just calling it real part, it may not be real part, whatever. So one of this part is 0, and then I am saying that it is sufficient to assume that under the summation for each I, this is 0. So then I have actually arrived at the next set of equations, which is now little bit simpler. Now what I am going to do, I am going to say that within this equation, now I have gone to this equation, my delta is arbitrary. That is all I am going to say. And I want to write this equation in a form which is delta chi I star, sum f of 1, chi I 1, and now his question will come. We will see, don't worry. Delta 1, I am now writing it in full form, minus sum over j, this second last term only I am writing it separately, delta chi I star 1, chi j 1, delta 1. You agree? If I can write it in this form, then I am in the business. Because what I will say, for all delta chi I, if this is equal to 0, then I will say that this minus this is equal to 0. Right? Remember, this is energy, so everything is integrated. But if I have to write this in this form, you can see that already f of 1 is h of 1, that is no problem. The second term onwards, integration over d tau 2 has to be performed explicitly. And I said that last time. If you explicitly perform the integration over d tau 2, this is actually a function of 1. So that is what I wrote. So all the function of 1s I have collected. The question is, can I write this as chi I 1? I don't have to write initially. I could have simply said some g of 1, the whole thing. That will satisfy you for the time being, and I will see how to write that. So that is what I actually said, that if something times g of 1 minus this equal to 0, then I can say that g of 1 minus integral this chi j 1 is equal to 0. So if this is, let us write this now. What is g of 1? We will write it down a little bit later. So let's write delta chi I star 1 tilde again g of 1 beta 1 minus sum over j lambda ij delta chi I star 1 chi j 1 beta 1. So we will see what is g of 1. G of 1 is basically all these quantities except for this quantity integrated by d tau 2. That is all that you need to know. Okay? But if I can write this for all delta, Then I made a statement, first to understand the statement, that this quantity minus this quantity is equal to 0. Because I could have punched this quantity inside this and could have said that the whole thing is equal to 0, because this is also a function of 1. So I did not do it. Only lambda ij has to be written explicitly. So if this is equal to 0, then for all arbitrary delta chi I star, note again, I have always doing delta chi I star, and that is same as doing a variation in delta chi I, because they are complex conjugate. So then what would be my equation? G of 1 minus sum over j lambda ij chi j tilde 1 equal to 0. You agree? If I can write like this, whatever is my G of 1. Remember, in that last class, I had also said that when we did this delta chi I star 1, chi j 1 and the reverse, we made a complex conjugate. I had assumed that the lambda is a Hermitian matrix. Okay, just remember that. That was also a small point that I did not note today, but I had done it last time. Otherwise, you cannot write even there itself, when you wrote that as a complex conjugate, very in the beginning. Okay, so that is somehow assumed. So then we get, I can write an equation, if this is true, for all delta chi I star, this minus this is equal to 0. I hope all of you agree to this. This is a very important point. Essentially, it means if I have a delta chi I star 1, some quantity h of 1, delta 1 is 0 for all delta chi I star 1, it means h of 1 is 0. This is just like we say in the vector product. If all integral, remember vector product, a star 1, b of 1, delta 1 is 0 for all a, then the b itself is 0. We use this in vector product. In fact, very simply we use in the all scalar product of the vectors, ab equal to 0 for all a, it means b equal to 0. So this is the same thing I am doing now actually. We assume this because any arbitrary function, if it is integrated to this a given h of 1, this is not arbitrary, this is a given. Any arbitrary function, if you multiply by this h of 1 and integrate, and if it becomes 0, h cannot be 0, obviously. So then what has to, sorry, this cannot be 0, so delta chi I cannot be 0, so obviously h has to be 0. Okay, since it's arbitrary delta chi I, that cannot be 0. 0 is a definite, only a given number. So the only way this is possible if this is 0. And this is actually goes back to the scalar product of the two vectors of a and b. It is 0 for all a, it means b is equal to 0. It is very similar in linear algebra. If operator acts on a function, if operator acts on an arbitrary function to give you 0, then the operator is a null operator. Right? Remember? It is very similar. Okay? So the linear algebra, because that's a very strong condition. So that is what I am going to use, provided I know how to write G. That I will come to that. That's not very difficult. So I am saying that provided I know this, then my final equation will be a single particle equation. This is now a coordinate of 1. Remember, everything here was multiplied, but when I writing the equation, these are dependent on the coordinate of 1. Okay? So that something coordinate of 1 would be equal to 0, and that is what we will eventually call a single particle equation. The rest, the question that he asked is now involved in G. So when we analyze the G, so I have to find out, extract this one particle part from each of these by carrying out the integration over d tau 2. Carrying out the integration over d tau 2, and there his question is there that how do I handle, physically how do I handle the exchange part? Because there is something else that he knows, that in the G of 1 I want to write chi I of 1 on the right. Right now that knowledge is not there. But if you want to write, then how do I do? That was his question actually, if I want to paraphrase the question. So we'll see that. Right now I don't care how I want to write, because quite clearly this is a once I carry out the integration over 2, this is a function of 1. Exchange or Coulomb, both are function of 1. Okay, I am not writing this as something times chi I 1. I abandoned that. I want to write it in this manner, but right now I have abandoned it. I am just writing G of 1 so that you have no question. Okay? So let me write down this G of 1. I want to keep this, so I am not erasing this part of the board. So I am going to erase this. I am going to erase this part of the board. And then what I will do is to see that the first part of G of 1 is just this. Okay, so I can write down the G of 1 now. The first part of G of 1, if you just make an analysis from here, that I wanted to write, remember my equation generically looks like this: G of 1 delta 1 minus sum over j lambda ij delta chi I star, delta chi I star 1 chi j 1 delta 1 equal to 0. So that is what I want. So this part I am not going to touch. So now I am going to write the G of 1 by comparison. So what is the first term? First term is simply H of 1 chi I 1, right? So then first term will map. Is it okay? The first term is simply that. The second term, of course, is 2 electron integral. So I have to carry out the integration over d tau 2. Then only I will get a function of 1. Keep this here. So what will be now G of 1? Sum over j, right? Sum over j also has to be carried out, and that is already there. Actually, I can see from here. I need not go there. So again, I write the chi I tildes. So now you can see sum over j, I write it in full form: chi j star 2 1 by r12 chi I 1 chi j 2 d tau 2. Note that, sorry, d tau 2. Note that I cannot forget this chi I tilde 1, because that is a part of G of 1. G of 1 should be everything other than delta chi I star 1. So of course, only this part I can remove, or this part I can remove. So chi j star 2 1 by r12 chi I 1 chi j 2 d tau 2 is a part of G of 1. Is it all agreed? So that's my G of 1. Minus sum over j. Now let's look at the exchange. Chi j star 2 1 by r12 chi I 2 chi j 1 d tau 2. Agreed? I've just interchanged the right side. So that becomes my G of 1, the 3 terms. So I have just interchanged this part. So again, writing the tildes: chi I tilde 2 chi j tilde 1. This is chi j tilde 1. So up to this point there is no problem. You have any problem with this? There is no problem. So if I simply write it like this and then push this G here, that's my Hartree-Fock equation. Because once I put G, that's my Hartree-Fock equation. I already have the Hartree-Fock equation. All I needed was to write G of 1. So I have given you the Hartree-Fock equation. Huh? Again? Why? You have a 1 by r12. What is this multiplicative term? No, it's a space orbital. If they are opposite spin, that is 0. If they are same spin, spin will not integrate. There will be space orbitals of these, space orbital these, which has to be integrated along with 1 by r12. Because space or if I have a phi I star r r1, okay, 1 by r12 phi I r1 d tau 1, is it 0? Let's say they are orthonormal. Let's say it is ij. I don't care, even if it is there orthonormal. Is it 0? I mean, that's a very fundamental point. In fact, we do 2 electron integral. This is only coordinate of 1. We did 2 electron integral where this is phi j star r2, whatever is there. Not 0, because this space part depends on r. That is what you are repeatedly missing. Only the spin part can be taken out because your Hamiltonian is spin independent. Even that cannot be taken out if there is a spin orbit interaction in the Hamiltonian. But this 1 by r12 does not have a spin. So only the spin part can be taken out, and that is why repeatedly we are saying that the exchange comes only from the parallel spin. Because then the space part does not matter. Spin part will make sure that it is 0. Is it understood to everybody? Yes. Yeah, what is the last question? That's completely different. No, that's completely different. That is a completely different case. What is this algebra? That is only interchanging. I have not made anything 0. So I don't understand what is the algebra you're talking about. I just gave an example that this is exchange integral ij ji. If they are real orbital, I star 1, j star 2, j of 1, I. So they are all 1, 1, 1, 2. There is no star here. So I can simply interchange 1 and 2. So this is 1, this is 2, this is 1, this is 2. This 2 I can bring here. So this is equal to II, JJ. But 1 by R12 is there. This J star 2, this J2 and I2, I can flip. It is commutative. Yeah, but they are commutative. I think you are making a mistake of commutation and this. They are commutative with 1 by R12. So this can come. But I am not saying they are 0. Huh? Anything is commutative with that. They are all function of x. So every operator, function of x always commutes with an operator which depends on x. So this is a commutative operator. So I am only commuting. It is just that I have not written 1 by R12 explicitly, but it is there and there is no problem. So it has nothing to do with orthogonality. Okay. And then I said, then these are 1, 1, 2, 2. So I can further do a dummy variable interchange. So this is because of dummy variable interchange. Right? This is simply because they are real. If they are not real, you couldn't have done that. So the question is, they are real orbitals. Yes. So I hope you have given the right logic. I only want the right logic. But it has nothing to do with orthogonality. Then it should be 0, right? I think you are getting confused with commutation. Of course, they are commutative. Yeah, all these fundamentals will be absolutely clear. I mean, we do that all the time. That if an operator is a function of x, it commutes with another function of x. And that's what we are doing. Problem is only the momentum. The momentum guy does not commute with a function of x because it's a del del x. So whole problem of quantum mechanics comes because of the px. If Hamiltonian was only v of x, nothing would have happened. Then all functions would have been function of Schrodinger equation, eigenfunction. But unfortunately, no system can exist without a kinetic energy. And that is where the px guy will come and create a lot of havoc because it doesn't commute with x. Okay. So I think that those parts of quantum mechanics should be very, very clear. Now it's good that you are asking those questions because, yeah, initially I didn't understand, but it's good. All right. So if I have been able to write g of 1, all that I have to do is to plug in here. So let me plug it in here. And then I will explain what was his question actually, little later. Okay, but let me plug it in here. There is still no confusion, but he has something in his mind that the chi1 must be always on the right, which he is not getting for the exchange. So that is something that I will explain later. So now what I'm going to do, just write this g of 1 and write down the Hartree-Fock equation. So it is h of 1 chi1 plus sum over j integral. I deliberately write it in full form because of the reason. And then what I do is that anyway 1 and 2 commute, so I push this guy on the right because then it looks nice. Then I'm integrating over chi j2. D tau 2 I'll also finish and then write this as a phi chi1. I hope you understand that this is same as this. It is just that I am first completing the d tau 2 integration, then writing the chi1 because chi1 cannot be integrated. When I am doing the d tau 2 integration, chi tilde 1 is a constant. So it can come out of the integration sign. That's what I have done. Again, to be consistent, let's put the tildes. Okay? Then the next part, which is sum over j. Now the problem will come. what he is trying to say. Chi star 2, 1 by R12. Now the integral over 2 explicitly consists of chi I 2. I can't write chi I on this side. So it has to be actually chi I tilde 2. And neither can I write j outside because the sum is over j. So everything has to be done together. Chi j1, d tau 2. Of course it is d tau 2. It is still d tau 2. Equal to sum over j lambda ij chi j1. Okay. Some of the textbooks from the beginning they use this as a lambda ji, but don't worry about it. It can be used right from the beginning lambda ji or lambda ij. That doesn't matter. You continue to be consistent. That's all. All right. So again, putting the tilde. This actually is my Hartree-Fock equation. Okay, this is actually an Hartree-Fock equation, which is a somewhat non-standard Hartree-Fock equation than what you know, in the sense that this is not an eigenvalue equation of a one particle operator, because I'm not able to extract that one particle operator yet. First of all, this right hand side does not have an eigenvalue structure. The left hand side also, these two terms I am able to extract. But here I am not able to extract chi I tilde 1, so I can't write something acting on chi I tilde 1. Assume that this was a diagonal. Assume this was diagonal. I am still not able to write something acting on chi I tilde 1 equal to some number times chi I tilde 1. Because of this exchange term, and that was his question. Right? Am I right? Okay. So we'll see. But this is actually a Hartree-Fock equation. If somebody says this is Hartree-Fock equation, right, absolutely right. It's actually a very general form of Hartree-Fock equation, and this is what is called in general Hartree-Fock equation. Sometimes it is called non-canonical Hartree-Fock equation. You have also may have heard canonical and non-canonical. This is actually non-canonical Hartree-Fock equation. Though what is practiced in all the textbooks, all the program is a canonical Hartree-Fock equation. So we will actually later see how to convert this into a canonical Hartree-Fock equation, but this is correct. The result energy that you will get out of these chi I tildes after solving will be same as the canonical Hartree-Fock equation. The energies will be invariant. So this is correct. There is no problem with this equation. Let us only try to understand the equation now. Clearly, let's assume this is diagonal for the time being, so that the understanding would be very easy. And let's assume that this Coulomb and exchange terms are not there. Then what would happen in your equation? A very simple h of 1 chi I 1 equal to number times chi I 1, which is basically the non-interacting picture that I told you. Forget about 1 by Rij. Your Hamiltonian is sum over h of I, then your spin orbitals would have been eigenfunction of h of I. That will come if you neglect these two terms and make this diagonal. That's important. So it's, you can see that that structure is already there. But because of the Coulomb and exchange, we ask this question, is it the best one? Now we have got the answer. This is not the best. This is the best because we have applied, we have obtained this by variation method. Remember,